My name is Dan Bonnet, and I'll be taking you through assignment 2.2 about the responses of the body systems to steady state exercise. So what actually is it? Well, in a nutshell, it means the supply of oxygen to the muscles meets the demand for oxygen by the muscles, which produces a clear balance. So a person's heart rate is how many times their heart beats per minute. The average BPM at rest is 70, whereas someone like Mo Farah, it would be roughly 40 BPM. When you begin to exercise, your heart rate rapidly increases due to oxygen deficit in the muscles, which produces a steep incline, as you can see on the graph down here. Then during steady state exercise, your heart rate will begin to plateau because the supply of oxygen meets the demand. And then after exercise, the heart rate decreases significantly, which is the body repaying oxygen debt. Stroke volume is the amount of blood pumped by the left ventricle in one contraction. The average stroke volume at rest for an adult is 70 millilitres, and then during exercise, it can increase up to 130 millilitres. Compare this to Mo Farah, who has a resting stroke volume of 110 millilitres, and during exercise, it could reach up to 200 millilitres. Now, your stroke volume actually peaks during submaximal exercise and doesn't increase during maximal exercise. So venous return is where deoxygenated blood returns to the heart. It actually returns slower though. This is due to there being low blood pressure throughout the body. And there are certain factors that support venous return, for example, muscular contractions, but we'll look into further detail on that on the next slide. So one way venous return is supported is by pocket valves. These help stop blood backflow. So as you can see from the graph here, the healthy valve closes once the blood has passed. However, the damaged valve hasn't closed, thus producing dangerous backflow. Another way it's supported is the muscle pump. This helps because when the two skeletal muscles surrounding the vein contract, it squeezes it, forcing a lot of blood back up to the heart. And finally, the respiratory pump supports it because as we start to breathe faster and more deeply, the pressure in the thorax and abdomen build up, squeezing larger veins, making blood flow back to the heart a lot more fluid. Now, Starling's law suggests stroke volume can increase in response to the filling of blood in the heart. It can also increase due to greater contractions of the cardiac muscles during exercise. And for an elite athlete like Mo Farah, his muscle and respiratory pump would be a lot stronger than the average. Therefore, there would be an increase in blood returning to the heart. So really, you could say that Mo Farah supports Starling's law. Now, cardiac output is the volume of blood pumped out the heart in 1 minute and is often referred to as Q. It's calculated by multiplying the stroke volume by the heart rate, and so the average output at rest will be between 4.8 and 5 litres, but during exercise it can reach up to 20 litres. Mo Farah's resting cardiac output would be about 3.6 litres, which is actually better than the average because more oxygen can travel around in his blood a lot more efficiently. During steady state exercise, however, Farah could actually have a cardiac output of up to 40 litres. So as we can see from this graph, when you begin exercising, your cardiac output rapidly rises to solve oxygen deficit, as well as carbon dioxide is being released. Therefore, to remove this, more blood must be pumped around the body, so it's replaced with oxygen. And then during steady state exercise, however, it plateaus before decreasing because of oxygen debt. Now on to blood pressure. So it's defined as the pressure of the blood up against the walls of the arteries, and there are two forms. Systolic is the pressure of the blood leaving the heart, whereas diastolic is the pressure of the blood returning to the heart. Here's a quick chart to show the ideal blood pressure, which should be 120/80 mmHg, which is what blood pressure is measured in, which is down there. And then here we have a picture of someone using the actual monitor. So the last aspect of the CV responses is blood flow. The vascular shunt is a mechanism where your blood vessels contract in places where the blood isn't required. This is so they're ready to force the blood or shunt the blood to places or muscles where it's actually needed. Next we have vasodilation and vasoconstriction. So during steady state exercise, our vessels go through vasoconstriction. This is so your blood pressure and blood flow increase. However, as the oxygen levels drop due to muscle use, the vasodilation occurs and lets more blood flow through, which decreases your blood pressure. Then for someone like Mo Farah, his vascular shunt would be more efficient than ours, sending more blood to the working muscles, which increases the chance of CO2 being removed, letting his muscles work for a lot longer. Here's a quick pie chart to show the total cardiac output at rest compared to the total cardiac output during moderate or steady state exercise. And then now we're going to move on to the respiratory responses. So breathing rate is how many breaths you take per minute at rest, and the average amount is between 13 and 16 breaths. But during exercise, it can increase to between 40 to 60. Our breathing rate increases during exercise because we build up CO2, so having more breaths gets in more oxygen and removes the CO2. Mo Farah very much supports the graph here during steady state exercise, as his breathing rate plateaus and so stays at a constant rate. As well as this, the amount of breaths he takes would remain the same, which would be about 60 breaths per minute. Therefore, more CO2 can be removed, enabling him to run for longer. Now, tidal volume is the amount of air that enters the lungs during normal inhalation at rest, and the average is 500 millilitres, but for someone like Mo Farah, during exercise, it could increase to between 2 to 3 litres. However, he's an elite athlete and so trains to increase his tidal volume. This means he has deeper breaths, allowing him to have a lot more oxygen supplied to his body. Tidal volume increases rapidly during exercise to deal with the oxygen deficit because deeper breaths means more entering oxygen. However, during steady state exercise, it will plateau because again, the supply of oxygen has met the demand by the muscles. Now, the oxygen dissociation curve shows the relationship between the percentage of oxygen saturation of blood and the partial pressure of oxygen. The reason the line curves off to the right is because during steady state exercise, the temperature in the blood and the muscles increase and the blood pH concentration level decreases. This means it's becoming more acidic. Due to these changes, the oxygen hemoglobin dissociation curve is affected, allowing oxygen to be removed from the hemoglobin into the active muscle. Now, Mo Farah would be working so hard in steady state exercise that the kinetic energy of his body will increase the temperature of his muscles and blood, and the pH concentration of the blood will decrease further than any average adult. This will then mean that the curve will shift even further right, allowing his oxygen to be transferred from the hemoglobin into his active leg muscles. So overall, a greater dissociation is required to increase the supply of O2 to the working muscles. Next, we move on to internal respiration. So this occurs in the respiratory membrane in the tissue and is the process of diffusion, which is when substances diffuse from a high concentration to a low concentration. So oxygen diffuses from the capillaries into the working cells in the muscles, and CO2 is vice versa. This is because there is a high partial pressure of oxygen in the capillaries and a low partial pressure of CO2, as well as a high partial pressure of CO2 in the muscle cells and a low partial pressure of oxygen. Here's a quick diagram to show the tissue cells and how the oxygen from the hemoglobin goes into the muscle tissues. So a diffusion gradient is what the substances move down. The diffusion gradient of CO2 is high between the muscle cells and the capillaries, and the gradient of O2 between the capillaries and muscle cells is high. This allows the CO2 to diffuse from the muscle cells into the capillaries and O2 vice versa. So now external respiration. So this occurs at the respiratory membrane in the lungs at the site of the alveoli. There is a high partial pressure of O2 in the lungs with a low partial pressure in the blood capillary, and a high partial pressure of CO2 in the blood capillary with a low partial pressure of it in the alveoli. So this means O2 diffuses into the blood capillary and CO2 diffuses into the alveoli. Now, our hemoglobins in our red blood cells bind with oxygen molecules when they diffuse into the blood, making it oxyhemoglobin, which is how oxygen is transported through our body. Now we'll move on to our respiratory controls. So the medulla oblongata in our brain controls our respiratory control center, otherwise known as RCC, and it controls our breathing rate and depth. The RCC consists of two centers: the inspiratory center, which stimulates inspiratory muscles to contract at rest and during exercise. Then the expiratory center stimulates additional expiratory muscles to contract during exercise. However, it doesn't do this during rest. But in order for these changes to occur, the neural factors of the body must detect them and send messages up to the RCC. So proprioceptors are located in the muscles, joints and tendons, and they detect motor movement increasing. Chemoreceptors detect chemical changes in the body, such as increased CO2 and decreased pH concentration. Baroreceptors detect the stretch of the lungs and inform the RCC about the state of lung inflation. Then finally, thermoreceptors detect increased temperature in the body and then send a message to the RCC to inform it.